So I did this calculation, the derivation of the electric field due to a charged ring, and I'm going to do it again. So in the last version, the I just focused on the electric field along the z-axis. So if I imagine that the ring's in the xy plane, and then the z-axis would be the axis of the ring, and you can actually get a full expression, a full calculation for this for the z component of the electric field as you move along the z-axis. But what if you're not on the z-axis? Then it's a pretty tough problem, and now I'm going to solve it because I like to solve problems, and it's going to be fun. So this is. Let me turn this off and let's get to work. We're gonna do this numerically because that's how I like to do stuff. So let's see, turn that off. Here, let me just explain what we're gonna do, and then we're gonna switch over to Python. So here is my ring, and then here's the side view right here. Now imagine that I want to calculate the electric field at this point right here, which is not on the z-axis. Okay, so that means that I have this ring I'm going to break into n number of point charges. Actually, let me write that down in so I won't forget. I got to write that expression. How do we break that in? What I'm going to do is first find the vector location of Q. So I'm going to call that RQ. I need that. And then I need the vector location of the observation location, which shouldn't really change for this particular calculation. And then I'm going to find this vector, R. And so R is equal to the final position, R observation location, minus RQ. Once I do that, I can use my equation for the electric field due to a point charge. 1 over 4 pi epsilon naught, that's just a constant. The charge, which is going to be just dq, divided by the magnitude of that R, and then I'm going to have to find the unit vector R hat too, because I'm going to get actually a vector value for dE right here. Once I get that, then I can move to the next point in my ring and do it again, and then the total electric field, E total, at that point, is going to be equal to the sum of dE. So it's going to add up over my values of n, and once I get done, I'm done, right? That's an n. So let's write down these steps. Step 1, break the ring into n pieces. So let's just imagine that I want to break this in. I know I need, and let's see, next is find R. Find RQ. That's the step right there. So I know I want to break this into n pieces. Let's call this the origin right there. And I'm going to put a piece right here. Well, where's the next piece going to be? And I need to know where it is and what's the value of the charge. So first, the charge dq is easy. I use lowercase q. dq is going to be the total charge q divided by n. And I'm going to use the total charge of q equals 1 nanocoulomb and r equals 0.01 meters, because that's what I did before. So I can find the charge on each piece just divided by the number of pieces I want to break this into. Let's call that 10, whatever you want. We'll change that. Okay. Now, how do I find the next piece? Well, if you think about this, if I want to move around in a circle, then I could find this piece right here. I could say RQ equals the value of R, which is just the radius, times the vector cosine theta sine theta 0. That's my vector notation, right? Because this is going to be my x value is going to be r cosine theta, my y value is going to be r sine theta, so I just need to know theta. So if I do that, I could say I'm going to start with theta equals 0, and then d theta equals 2 pi over n. I think this is going to work. So then if I want to find my next piece, I just calculate the r value based on theta, and then I move my theta around until I get back to the whole loop. And each place I'll even draw a little circle. I'm going to do everything. I'm going to draw a circle for a sphere for each little point charge, and then I'll calculate the total electric field as a vector also. So break it into ring into pieces, find RQ, find DQ, which I know, that's easy, and then find DE, and then add them all up. and that's what I'm going to do. And I don't actually even know exactly how I'm going to do this because I'm just playing this by ear. Okay, but let's switch over here to Python. And yes, I'm going to give you the code because that's what I do. And I have nothing here. I'm starting from scratch because that's the way we roll. So let's just start with some constants here. K equals 9 times 10 to the 9th. Q equals 1 times 10 to the negative 9th, right? Because I said that was a charge. R equals 0.01. And now I need N. So let's say N equals 10. So I can get dq equals q over n, and d theta equals 2 times pi divided by n, and theta equals 0. So I just want to make a ring of spheres. Yeah. Okay, so let's just say let's just try this. We're going to do it different ways. While theta is less than or equal to, no, less than 2 times pi, colon. And I'm just going to make a point. I should save this. Numerical E ring. That's a terrible name. Fine. Okay, so the first thing I'm going to do is make a sphere. Let's just draw these spheres. I can add them into a... Do I want to put it in a list? I don't have to. Nah, I'm not going to. So let's just say sphere position equals r times vector cosine theta, sine theta, 0. The radius of each point is going to be equal to, let's put something like 0.001. That might be too big. Well, whatever. And then I'm going to move my theta. Theta equals theta plus d theta. And that should be it. I should make these things. I think those are going to be too big. Save it and run it. Yeah. Boom. Ha! Did it. Okay, in Python, the default axis for the z-axis is coming out of the screen, but there's my thing. That looks pretty nice. What if I change this to 100? Check that out. Okay, so I do want to make the radius a little bit smaller, even though that's fine, I think. Let's make this 0.5. Yeah. See how easy that was? I think I might have, there's a chance I could have one extra charge in there, but if I break this into 100 pieces, what one charge? I guess I should count them. Should I count them? Let's say, let's do that. Oh, I went forward. I went backwards. No, it didn't. Okay, run it. I don't know what it did. Okay, let's say count. Count equals 0, and then each time in here, I'll just add 1 to the count. Count equals count plus 1, and then print count. Because of the way I set up my loop, it's possible. 101. See, I told you. How could I fix that? Wow. Okay. So, I could fix this by... Oh, no, I didn't. I made a sphere, I updated theta, and then I counted, and I got back up here. I actually don't think I do. Count is 0. I'm going to just go on with it. Because, you know, I feel like I should. Every time it prints a sphere, it counts. That's fine. Let's just leave it. It's not going to be perfect. You can fix it for homework. Okay. Okay. So now I make my spheres. Now I need something else up here. OBS equals sphere. Position equals vector. Let's call this. We can change this. Vector. I'm going to put it at 0.01. 1, 0, 0.05. Radius equals 0.001, and let's make it yellow. Okay, so that's where I want to calculate the electric field. And there it is. I kind of feel like I want to move this thing because I'm going to. So let's put this on the XZ plane. So I'm going to put this at like that, and then this will be that way my X value will be my big one, I think. So let's put this at 0.05. Let's just run that, and let's put this 0.1. No, did that backwards. This would be sine, and this be, no wait. No, I'm sorry, that should be cosine. I just make mistakes sometimes. So I want the x-axis to be this. There we go. Okay, and that's not quite on the x-axis. That's fine. Let's make it a little bit closer. Let's make this 0.2. 0.2 on the x-axis. Oh, and let's put this on the y just so it's easier to see. .01. Oh. Okay, good. I'm going to calculate the electric field right there. Okay, I have my spheres, and they all have locations. Let's actually do this as RQ equals, and I'm just going to copy this thing right here. I'm going to cut it, and then I'm going to say position equals RQ and run it. And so what that does now, I have a variable location for each one of these things. It's going to be easier to deal with. The spheres I actually don't even need to draw. Up here, I'm going to say E equals vector 0, 0, 0. That's going to be the total electric field. What I'm going to do is add my electric fields in this loop and to make a comparison. So I have my RQ. I already put that on my list, right? Break the ring into n pieces, done that. Find RQ, done that. Calculate DQ, done that. Now I just need to find DE. Let's write that out as an expression. DE equals K times, I need to find R. So R equals observation.pos minus RQ, right? That's exactly what I wrote in the paper, so it's the same thing. Oh, and I'm covering up my output with a picture of me that no one really even cares to see anyway. There. So now I can say K times DQ times the unit vector R, which is going to be norm R, divided by the magnitude of R squared. Now I'm going to add that, E equals E plus DE, and then that's going to be it. Go through the whole thing, print E. Let's just see if it works. Okay, so there's my value of my electric field. And the real test is going to be in just a second. Let's make that as an arrow. Let's say E arrow equals arrow. Position equals observation.pos. Axis equals E scale times E. And I do need E scale, which we'll get in just a second. Equals, let's say, 1E negative 3. I'm just picking something there. And then the color, I guess I should make it yellow. Color equals color dot yellow dot run. Too big. And so the deal here is that, see, there's my ring, and I'm drawing this arrow for the electric field as an actual arrow in distance. And so I'm using the size, the magnitude of the electric field as the size of the arrow, which is just crazy too big. Let's make that even smaller. Okay, that's pretty good. So there's my electric field due to a ring at that location. Okay. Now, is this legitimate? Well, we can make a graph of the electric field along the x-axis as a function of x. and then compare that to my other graph, which I already actually have right over here. Here's the electric field due to a ring, same ring, along the z-axis. But if I get the same shape, I'm not even going to, I could put these both on the same graph. I'm not going to do that. Let's just make a graph of that. So to do this, it'd be easier to make a function. So let's make a function called, and I'm going to call it EZ. Okay. So, and this is not the best way to do it, but who cares? And that one's being there too. I'll leave the in outside of the function. Def EZ. And what do I want to give it? I want to give it, let's just pass in the location, the observation location. RO. RO. And then so down here, I'm going to put the observation location is, oh, this needs to be a colon. And I need to indent all this stuff. I don't actually need to draw. Let's not draw. Yeah, let's not do that. And let's not do this. I'm turning everything off. I'm not going to draw anything because it'll just slow everything down. But I do need to, I tabbed into that, tab into that, tab, 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 and I'm not going to draw. Okay, so now up here, I just need to make a couple changes. That's fine. RQ is that's fine. R is just going to be, now I don't have OBS anymore, I just have RO. And then this is that's fine. That's fine. I think that works. Okay, so let's just let's just run this. Say print EZ for vector. I picked. Let's put 0, 0, 0 because I know that should be 0, and let's see if that works. We did that before, right? And it didn't. See, theta hat. Oh, theta equals 0. I need to put that down here. Theta equals 0. I think that works now. What the? No, undefined. Easy. R, I gave it past that. Oh, I never returned anything. Dummy. Okay, return E. Okay, and it's not 0. It's not even close to 0. That's close to 0. Oh, 0, 0, 0. I feel like I really messed up. Okay, I'm just going to delete everything. I mean, what the heck, right? And let's just make a function called def e ring. And I'm going to pass into it, I've already have the size of the ring. I'm not going to change that. I'm going to pass into it our observation location. And then, so the first thing I'm going to do, starting all over from scratch, I need to say what theta is. Theta is equal to 0. D theta equals 2 pi divided by n. E equals vector 0, 0, 0. And then I'm going to say while, I feel like I'm missing, dq equals q divided by n. While theta less than 2 times pi, rq equals r times, oh, what did I say here? It was, let's put it back in the z direction, because that's the way I'm thinking right now. So it's going to be vector cosine theta, vector sine theta, 0. And then r, O, I already know it's what I'm passing in there. So R is going to be RO minus RQ. D, I need, ooh, I got that. DE equals K times DQ times norm r divided by mag r squared. And then E equals E plus dE. And then theta equals theta plus d theta, which I have. And then return E. And then print E ring 100 vector 0, 0, 0. It should give 0. Negative 900. Oh, you know what? That's because I do not have, I had it right the first time. It's because I do have that extra piece in there. So let's just fix this by, if I put this at 1,000. Oops, what did I do? This one. If I put that at 1,000 and run it, see, now it's smaller. So I am getting that extra piece in there, and the best way to fix any problem like that is to worry about it later. But for right now, I'm just going to have 10,000 pieces, and then that one extra piece doesn't really matter. Ha! Okay. So now I want to make a graph. T graph equals graph. Title equals EZ. Let's just put it like that. X title equals Z in meters. And then Y title equals, what was I going to call it? EZ in newtons per coulomb. And then I can say F1 equals G curve, color equals color dot blue. And now I'm going to say Z equals negative 0.05, DZ equals 0.00001. I'm doing the exact same thing I did before, right? I'm actually doing this same thing for this graph, and I'm going to go up to, I'll go up to 0.07, but I'm not going to plot this. I'm going to plot my function, okay? So it's going to be while z is less than 0.07, I'm going to calculate EZ. EZ equals, I guess I should technically say that, E ring, 10,000, see it's 1,000, vector 0, 0, z, and then I'm gonna say this is just the z component, so that returns a vector, so I'm gonna say dot z, it's just gonna give me the z component of that vector. Now I'm gonna plot this. If this works the first time after I made that mistake, I'm gonna be happy. F1 dot plot z EZ, and then increase z. Z equals z plus dz. Please work. Save. Okay, so you see it's taken a while because I'm doing this 10,000 times, and that was a mistake. So every point, oh, look at that, it worked. Look at that. There's my graph for my numerical calculation. There's my graph for my analytical calculation, and they're pretty much agreed. Let's just check this point right here. This is at xz equals 0.07 as a maximum of 3.45. That's pretty much the same thing. This is what we call in physics winning, okay? So there you go. I did break it up, and I could do this. This program can do it for any location. No, not that one, this one. For any location. And yes, I should fix that extra charge problem, but I'll just worry about that later. So there you go. I will include the code for this down below. I'm going to do, the next thing I'm going to do is electric field due to a plate, a disc. And I will talk to you guys later.